Hello everyone, welcome to this keynote presentation. My name is Mustafa Barzekeri from the Department of Mechanical Engineering at KU Leuven in Belgium. In this presentation, I want to talk about the applications of high-performance computing in biomedical engineering. And as a use case, I want to show you the main line of my research on the modeling of biodegradation behavior of metallic biomaterials. To begin with, I want to have a general overview on high-performance computing, as HPC, an abbreviation, which is actually driven by the need for more computing power for performing simulation on higher scales and on simulating bigger models, let's say. And this is achieved by leveraging and taking advantage of computing resources that are usually distributed, in a distributed way, that are really scattered in a distributed way to solve complex problems. And HPC comprises of software components and hardware components. The software components are usually dealing with performing computations in parallel on lots of smaller tasks, smaller jobs on different computing elements, and as I said, they are usually distributed. But on the hardware side, beside these advanced architectures of CPUs and this kind of stuff, what actually matters a lot is the very fast network that provides this communication infrastructure for these compute elements to interact with each other. And why do we need HPC? That's a trivial question, but yeah, it has several answers. But actually, we want to complete a time-consuming operation in less time, or we want to perform a high number of operations per second. And that's actually, a combination of these two is what we are seeking for in HPC, and especially for the things that I want to show you today in biomedical engineering applications. And typical HPC workloads, there are wide range of different applications you can imagine for HPC, for high performance computing. But the most famous ones are in physics, in astrophysics also, for biosciences, bioinformatics, genomics, and artificial intelligence, as well as chemistry, molecular sciences, lots of applications in this regard. And then computer-aided engineering, which is actually the topic of this presentation, in mechanical engineering, in aerospace, in biomedical engineering. And also computer science, mathematics to develop high-performance algorithms and also solving complex mathematical problems. And big data analytics and financial and economical modeling for risk modeling, this kind of stuff. And weather climate forecasting and simulation on climate change, in this regard. And also cybersecurity and advanced graphics, including rendering of simulation results in computational modeling. And also a lot more. So there are so many other applications you can imagine for HPC, but these are the typical workloads. And supercomputing computational sciences, as I said, it's driven by the need for solving more complex problems in less time. And for doing that, you can imagine that, one common solution, things that comes from common sense actually, is scaling up. And scaling up means that we employ faster CPUs, larger memories, or more advanced hardware and software tools. And in this way, you can easily, increase the performance of applications without modifying the software, let's say, because you scale up the facilities, the equipments. But another technique, which is actually what we are talking about today, is scaling out. And it means that you break your application into smaller jobs, into smaller tasks, and then you can run them in large parallel infrastructures. And actually, so you can say that, we have many small to medium jobs, but they are running in parallel. And as a result, you can increase the performance and decrease the runtime. And it resembles probably in your mind the concept of parallel computing. So high performance computing is synonymous to parallel computing. And parallelism is available nowadays at many levels. Even on your laptop, if you have you definitely have a multi-core CPU, and it means that parallelism is available to you even on your local machine or laptop, because you can employ the multi-cores of the available multi-cores to speed up computation if you can parallelize your computing, your simulations, your models, your codes. But what is really important to consider, to keep in mind, is that all HPC machines are parallel architectures. So if you want to go for high performance computing, you should go for parallel computing. And fundamental parallel architectures, I don't want to go for jargons, but the fundamental architectures are shared memory systems and distributed memory systems. Shared memory systems are like the CPU, as I said, on your local machine, on your laptop. The different cores have access to the same data because they are on your RAM, on your memory. But in distributed memory systems, you have different CPUs, and as a result, they have their own memory. So it's common to say that the memory is also distributed. And the HPC, the typical HPC processes include both systems. So in order to program HPC systems, you need to deal with both types of systems, and the shared memory and distributed memory. And what matters a lot in HPC is benchmarking and scaling tests to see that your employed techniques for parallelization actually work. And then this kind of benchmarking would help you to improve the efficiency, speed of, and performance of the developed codes. And for HPC in biomedical engineering, there are a couple of obstacles, and one of the main thing is in biomedicine, biomedical engineering, much effort is put into the model credibility and to validating the models and proving that these models can work and can be used in clinical trials for medical decisions, this kind of stuff. So this is actually the main concern in simulation, computer simulation and modeling in biomedical engineering. And as a result, less effort and is put into scalability of the models. And while it has definitely a high gain and for the field, and as you will see in the other presentations of this session, there are great examples that they have employed the HPC techniques to simulate larger scales and to simulate things that that mimics the physics of the real world much better. But yeah, generally speaking, scalability of models and high performance computing things has gained much less attention in this field. But the potential of impact of HPC can be like employing more quantities of data and parameters. So we can employ more, we can, take into account more aspects of the real phenomena that we are going to model. And this will lead to, more detailed models, and as a result, more detailed simulations, which will be more predictive, let's say. And this will enhance the clinical decision making because the models would be, as I said, more predictive, and they can be employed to make better decisions and deliver better therapies. But what matters a lot in this regard is it will be on shorter time scales, which means that, we want to employ more quantities of data, and we want to perform, simulation on bigger scales, on bigger systems, and enhance the therapies, delivery of therapies and decision making. But it will be done on shorter time scales, and this is where HPC comes into play, actually, that we want to decrease the runtime and increase the performance, so you will have the results faster, much faster, and in comparison to the scales that is very common in academia and also in industry. But as the last note in this general introduction, I want to point out the role of free and open source software, which is actually undeniable in the progress of HPC things. So it's very difficult to imagine where HPC would have been without open source tools and open source software. Because beside the freedom and flexibility in HPC, that's quite famous that this kind of software will bring a flexibility into any field, but which is also the same for HPC. But beside this, it's also nice to see that a large number of relevant programs that are being employed in HPC are all open source, including the operating system tools, low-level libraries, job scheduling and load balancing system, and more important than them, the high-performance libraries, math kernels, solvers, tools, PETSI, Trillinus, all these big libraries that are used and are widely used in numerical computing for numerical simulations, for computational modeling. They are all open source, or let's say 99% open source. So, as an example in this regard, to demonstrate the power of HPC in biomedical engineering and tissue engineering, I want to show you an example of a high-performance computing project that is related to computational modeling of biodegradation behavior of degradable metals, in which, to increase accuracy, I will show you, we really need to employ HPC techniques. Otherwise, we need to wait for ages for simulations to complete. So as a very general introduction to the research to demonstrate its necessity, I can say that when we talk about biodegradable metals, we are usually referring to magnesium, zinc, and iron. And we mean that, we put some materials inside the body and they gradually disappear and get absorbed by the body and replaced by new tissue or bone or whatsoever that is growing there. And they have great mechanical properties, biological properties. But the problem is we need to tune the release profile, because it's really difficult to predict how they will, they release material and how they disappear, how they degrade inside the body. So this degradation behavior should be optimized and tuned for different applications. As you can see, they have different applications for various fields, for orthopedics, for dental applications, for cardiovascular things, but the profile should be optimized. So the challenge of the research, the challenges that the research is trying to address is tuning the biodegradation rate to the generation of the new tissue. And it can be solved by constructing a mathematical model of the biodegradation process that can be coupled with a tissue growth model. So we have the degradation of the material and the growth of the new tissue. And we should consider the different environments, including like the in vitro environments in the lab, or in vivo environments, in vivo situation inside the body. So the model should capture these situations. In order to do that, the workflow, this is a common workflow in most of the computational modeling projects, that the underlying sciences are converted to mathematical models, and then mathematical models to computational models. In this project, the underlying science is the chemistry of biodegradation, the physics of perfusion, because if you want to validate the models in vitro conditions, then we need to consider the perfusion bioreactor setups, in which you have a fluid flow, and then this should be considered, this should be taken into account. And also the biology of tissue growth. As I say, we want to also capture the biology of the tissue growth and its effects on the degradation. For mathematical models, we have partial differential equations. So the underlying sciences are converted to partial differential equations, mainly reaction, diffusion, convection equations, Navier-Stokes equations, and level set method. And the level set is actually for capturing the way that the material degrades. There is a moving interface, and then we want to capture it. And the computational models is a combination of finite element method and finite difference method, scientific computing libraries, and open source solvers. So the model should capture, from the perspective of chemistry, I want to discuss this only in this presentation. From the perspective of chemistry, the model should capture the dissolution of the metallic implant, which is actually this part. You can see that the metallic implant in different solutions, and the dissolution of this metallic implant, formation of a protective film, which has different composition in different, in different environments, let's say. The presence of effect of different ions in the medium, depending on the medium, you will have different ions, different chemical components, and they have different effects on this layer and also on the underneath. And also the change of pH, which can be a good criterion to validate the models. To construct the mathematical models, this chemistry should be converted to the mathematics. And in order to do that, we can employ reaction, diffusion, convection, partial differential equations. And as an example, just for magnesium, this is more or less the form of the mathematics, the mathematical form of the equations, let's say. That's similar to this, we usually have 6, 7, 8, this more or less equations describing the chemistry. So this is actually how magnesium diffuses, how it gets convected, and how it reacts with the surrounding environment and also with different components. So this is the style, this is a form of the mathematical model in this work. But as I said, there are more PDEs. In order to construct a computational model, due to the complexity of the mathematical equations and the mathematical model, it's not feasible to implement this in sophisticated software programs and already available commercial solvers like ANSYS and Abacus. And as a result, we decided to develop our own solver using finite element method to discretize the PDEs. And as I said, we used level set method to capture the moving corrosion front. So actually, biodegradation is a sort of corrosion. And when something degrades, then you see that the interface moves. And we use level set formulation for capturing this. And this is why we need to refine the mesh on the interface, on the moving interface, to increase the accuracy of these numerical schemes. And this is actually how it works, that we refine the interface, we refine the mesh on the interface between the metallic parts and the surrounding mediums. In this case, you can see an example in 2D for a simple screw. But in 3D, then, it becomes very, very intensive because you have millions of elements. And that's why we need HPC for this. So to implement a computational model in the mesh generation process, we usually end up with 10 to 20 millions of elements, so quite a large number of elements. And for degrees of freedom, so when we want to implement it in software, in programs like FreeFEM for weak formulation, and then to assemble the linear system of equations to solve, for each PDE we have a degree of freedom of 2 to 4 million. So that's actually how it works in practice. And this is the reason that parallelization is essential actually for this work. So we employ a combination of two techniques: high performance domain decomposition and also high performance preconditioners and solvers. And also the I/O, the input-output of the results, is in a parallelized way for parallelized post-processing. So these are some, quick overview on some of the results that we have on this. So this is a simple screw degradation. You can see that that the white interface evolving is actually shrinking is the corrosion front, which is captured by level set, and you can see the release of materials to the surrounding, and also the way that we can capture the topology changes, the shape changes during the degradation simulation. This is a simulation for a jawbone plate, degradable jawbone plate that is degrading. You can see the release of material and also shrinking of the surface. And this is mostly for validation of the models, the release of magnesium ions, and formation of a protective film on a surface. As I said, this is something that is captured by the model. And this is another animation of degradation that are post-processed in two different ways. You can see the release of material and the way that the metallic block disappears. And from the quantitative perspective, we have compared the side corrosion product formations, in this case evolved hydrogen, as well as change of pH with the experiments, with the dedicated experiments that were performed with the computational models. And you can see that they are in a good agreement, actually. Okay, as I said, this has been achieved using HPC, because otherwise the simulation could have taken ages to complete. And I want to show you some more details on the parallelization approach that we employed. It includes first the distribution of mesh among available resources, so a sort of mesh decomposition, which has been done using overlapping Schwarz method. And also solving the linear system of equations. A finite element, leads to a linear system of equations. In this case, it consists of, millions of unknowns, and we use algebraic multigrid preconditioners for reaction diffusion systems, and then GM-RES iterative solvers to solve the system, as well as field-split preconditioner for fluid flow and Navier-Stokes equations. So the way that the mesh decomposition works is actually, as I said, using overlapping Schwarz preconditioner. And then, it's a sort of mesh partitioning, and then each partition is assigned to one CPU core for parallel processing. And these figures belong to a simulation with 170 CPU cores, or let's say MPI nodes. So for performance analysis, we did a sort of benchmarking on a simpler and a smaller system. So a setup with a ticker box, in which we solved only 3 PDs out of 8 or 7, as I said. And then the degrees of freedom for each PD is around 150,000, and then the number of elements around 1 million, 900,000. And for benchmarking, we use Wicked scaling, in which you double the problem size while doubling the resources, so the execution time ideally should be the same. So this is a demonstration of that. You can see that we double the problem size while doubling the cores as well. So, this is how Wicked scaling works. And also strong scaling, in which you keep the problem size constant and you double the resources in each stage. And ideally, the performance should be doubled in this test. So for Wicked scaling results, you can see that we perform it with up to 8 cores to see how it works. And this is the speed up and parallel efficiency, a proper parallel efficiency. And to analyze this, actually, the common rule is actually Gustafsson rule, in which you have an ideal performance, an ideal speed up, and then by interpolating this line on the speed up results that you have, you can compute the sequential part and parallel part of the code. In this case, it was 82% of parallel part. And also for strong scaling, you can see that we have performed the simulations to up to 300 of cores. And then for speed up and efficiency, you can see that efficiency is almost half with 300s, which makes sense because you have overhead in lots of things, for memory overhead, for communication overhead, and this kind of stuff. And the common rules that is usually used is Amdahl's rule with a different equation. So when interpolating the equation, we will have the sequential part, which is actually the value of f here, and the parallel portion to be 99% and 1%. So it shows that the code has a high potential to be parallelized. And beside this speed up and efficiency, we can see that the employed technique is actually a good scaling performance. And also for preconditioner and solver performance, as I said, we have compared different preconditioner and solvers, and in the end, we came up with the algebraic multigrid and GMR solver, and this is actually the reason that we saw the best performances is achieved using this combination. And as a final note, I can say that, that all the developed codes and employed tools are all open source. So I have used a wide range of different libraries and tools in this research, but they are all open source. And as a result, the final code that we have developed is also open source and freely available on GitHub. So you can check it out if you are interested. So in this presentation, we talked about the necessity and importance of high-performance computing in biomedicine and biomedical engineering, and the reasons why it has received less attention, let's say. And as a use case, I showed you a quantitative computational model to simulate a biodegradation behavior of metallic implants. And then we discussed some of the performance evaluation tests of the employed parallelization approach to increase the scalability of the models. Thank you so much for your attention. Feel free to reach out if you have questions or comments on this presentation.